In this video, we'll see how we can implement this abstract data type called Q using a linked list as the underlying data structure. Okay, so the easy approach would be using a doubly linked list. So if we use a doubly linked list, then you remember that in a doubly linked list with a tail pointer, then all the operations of uh, removing an element or a node from the beginning or the end of the linked list called pop front and pop back, and adding a new node to the beginning and end called push front and push back, and also checking the value in the first node and last node. All of them can be done in constant time. Okay, so the only thing that's important in this case is going to be that since we are looking at the behavior first in, first out, you have two options. You should either push or NQ to the front and pop or DQ from the end of your linked list to get the behavior of first in, first out, or do the opposite, which means you push um, or NQ to the back of the linked list and pop or DQ from the uh, front of the linked list. Okay, so both options are, equally good, and whichever you do, because it's a doubly linked list, you get constant time for all operations. Okay, now to be more specific, remember push front is your NQ. Okay, so this is your NQ and this is your DQ. So obviously NQ and DQ are constant time. We discussed this when we were discussing doubly linked lists. And the other operations that we had, empty. So empty is checking to see whether your doubly linked list is empty, and that's just checking to see whether both head and tail are null pointers, and that's all, right? So all operations are constant time. The other thing is making sure that this behavior is, satisfied. And it is because if you think about it, this is the head. Let's say we are going with the first option. So head and tail. So you start with an empty. Let's start with an empty doubly linked list. So at the beginning, it's empty. So head is null and tail is also null. So this is head and this is tail. And let's say, for example, after creating this empty Q, which is implemented using a doubly linked list, then we NQ, say 7. Okay, now we are going with this option, which means NQ means push to the front. So I create a new node. It contains 7 as its key. And then remember the next and previous pointers. Since this is the only node, next is null, previous is also null. But head and tail are not null anymore. They both point to the same link. No, the only node that we have. Okay, and then we NQ again, say 8. Okay, and then what it means is that a new node will be added again to the front, because NQ means push to the front, with 8 and 2 pointers for next and previous. Now, since you are pushing this to the front, it means that this will be the new first node, right? Which means that I need to change a couple of pointers here. First of all, head should not point to this node anymore. Instead, it should point to this new node because I'm pushing this to the front of the linked list. The other thing is the next pointer here should point to what's now the second node. The previous should be null. And finally, the previous pointer in the second node which is null at the moment, should not be null anymore. It should point to the new node that we created. So it will look like this. Okay, so that's 2NQ. Now let's do a DQ and let's see if the first in, first out behavior is preserved here. Okay, so what is DQ? DQ is pop from the end or pop back, which means remove this node and return the data. So when I DQ, this node will be removed and 7 will be returned, which is exactly what is supposed to happen because 7 was the first key that we pushed into the key. Okay, so first in, first out. And obviously, all these operations are constant time. We had this discussion before, so let me not get into that one more time. You can check the video on doubly linked list to make sure that you understand why the running time of these operations, all 4 of them, is constant time, right? So you either the bottom line is if you're using a doubly linked list to implement a queue, everything is fine as long as you push to one end and pop from the other end. Either push front at your NQ and pop back at your DQ, or push back as your NQ and pop front as your DQ. And in both cases, you get constant time for all your operations. And also, your capacity is not limited, right? You can add nodes at any time and change uh, the number of nodes as you are using this queue data type. Okay, so that was kind of trivial. Now, the more interesting case is if we want to implement a queue using a singly linked list. Okay, so how about if I want to implement a queue, but I want to be a little bit more efficient with my memory usage and use a singly linked list, right? Because if you can do this, then you're using less memory because each node has only one pointer. Also, it's easier to implement the single linked list as well. But let's see if we can get the constant time because that's crucial for us. We want all our operations for a queue to be constant time. So let's see if we can get that. Okay. Now, the same observation holds here. If you want first in, first out, you should push to one end and pop from the other. Okay. So if you want first in, first out, you should either push to the front and pop from the back, or the opposite, push to the back of the linked list and pop from the front as your NQ and DQ, right? But here, the situation is not symmetric. If you remember, again, in a video about single linked list and runtime of different operations on a single linked list, if the single linked list has a tail pointer, then first of all, push front and pop front, these are fine. So push front, pop front, these are constant. But pushing or popping from the back is the one that is problematic in terms of the running time because you only have, you have the head pointer, right? And it's a singly linked list. So let me start with an example. Okay, so here is the place that we need to be careful. So we have a tail pointer that points to the last node. And if you want to pop from the back, then it means that you can use the tail pointer to delete this last node from the memory, which is fine, constant time. But then tail should point to the previous node. But the only way to find the address of this previous node, because there is no previous pointer here, is starting from the beginning and traversing the linked list all the way to the node before the last node. And that takes order and time. So pop back cannot be done in constant time in a single linked list, even if they have a tail pointer. On the other hand, pushback can be done in constant time because to perform pushback, Again, I'm just reviewing this because we covered this in detail in previous videos. But if you want to push back, you create this new node here, and then use tail to make this pointer, which is null, point to this new node. And then tail itself, you change the tail pointer so that it points to what is the last node now. And you can do all of this in constant time. So pushback can be done in constant time, but pop back cannot be done in constant time. In a singly linked list with a tail pointer, which means that this option is out. And if you want to use a singly linked list to implement a queue, uh, first of all, your singly linked list must have a tail pointer, and also your NQ will be pushback and your DQ will be pop front. So this is your NQ and this is your DQ. Otherwise, you don't get constant time for your operations. Okay, and so if you do this again, all operations are constant time or order one time. And still, there is no limit on how many nodes you can have. You get all the good features that you have with doubly linked list, but it's easier to implement because you don't need to maintain two pointers at each node. And also, it requires less memory because each node, instead of having two pointers, has only one pointer. Okay, now in the next video, we are going to use the other basic data structure, namely an array, as the underlying data structure to implement this abstract data type of queue.